Met yesterday with the other 45 lectures regarding development of exam 1. This is a copy of the information sheet which you will all be issued when you take exam 1. But I recommend that you download such now and make it available for you on our Canvas website, just so you know what you're looking at. You know the information you'll have handy and made available for you when you do an exam. Likely this is the same information. This information sheet will be the same for each exam. So go ahead and get yourself a copy of this right now. And jump start out getting ready for exam 1. Also, one of our good folks came to see me yesterday and made me aware that I made a typographical goof on Special Quiz 1. I fixed it. The corrected version of SQ1 is now available on the Canvas website. Simply put, regarding the John Dalton problem, I think part D was the part that contained the mistake. Question 3, it read, if my memory is right, on the original version, tell why, explain why the molar mass of G must be larger than the molar mass of N. That's the statement that has to be amended to read, tell why the molar mass of G must be smaller, not larger, than the molar mass of N. If you've been doing any of these exercises, exams, quizzes, whatever I think available for you, like remaining 3 SQs, 1 before exam, 2 before exam, 3 before final. See anything on there which you think is an error, holler. Believe me, if you think a mistake proves you're wrong. I make them. Not on purpose, believe me, but I make them. So again, if you see something that you think is wrong, tell me. So that at the minimum, I can take a look at it. Okay? Now then, one additional comment on writing reaction equations. That's RE. Last time we took a look at development of the reaction equation on the reaction that occurs when sodium is added to water. I expect we'll do that reaction later on. A demonstration. You will in fact see that reaction demonstrated for you when you tackle 2045 lab this term, assignment 5, part 1. Sodium water reaction will be demonstrated for you by a very famous movie star. Very famous. Me. The purpose of the demonstration is to get you to understand how to do redox reactions. At least in a more thorough fashion, that compared to what you will know about redox reactions when we talk further about such, when we wrap up our stuff for exam 1 and conversation on chapter 5. We've already talked about that to some extent. Now then, the main consideration underlying the sodium water reaction was that products, among the products were ions, specifically sodium ion and hydroxide ion. And in writing the material balance statement, we had to realize that without multiplication of reactant sodium by 2 and product sodium ion by 2, you had a statement which illustrated material balance but not charge balance. So it can't be an equation. To be an equation, any statement, a reaction equation, a statement must show material balance and charge balance. But without such, the system would be electrically not neutral. It would be therefore quite unstable, couldn't exist. All right, one more illustration. Here's a reaction, skeleton for such. showing the combustion of this material, whose name later on you'll likely learn as benzene, but I don't much care about names at this stage of the game. Has some interesting valence electron properties, specifically resonance. More on that later. This shows the reaction of material benzene combining with oxygen, say from the atmosphere air, with products being CO2 and H2O. If I've not yet said so, this material, which I hope you recognize as a hydrocarbon, because it has only carbon and hydrogen in its composition, on chemical reaction with oxygen, if the reaction goes to a set of conditions described as completion, the reaction of any hydrocarbon with oxygen will produce as exclusive products carbon dioxide and water. Those are the exclusive products produced by the combination of a hydrocarbon, chemical combination of a hydrocarbon with oxygen. Would you also likely recognize this reaction as a combustion reaction? This reaction statement parallels what takes place in your automobile engine when gasoline, a hydrocarbon. Although today's gasolines have ethanol mixed with it. But it used to be that gasoline was strictly isooctane. No ethanol contained within. So previously, gasoline was strictly hydrocarbon. So perfect combustion with oxygen leaves to produce CO2 and H2O is the only product. A high energy liberating reaction. When we get to chapter 6, we'll talk about a reaction like this from a thermodynamic analysis standpoint. And remind you that this reaction is strongly favored by producing products which have stronger covalent bonds than the reactants. And by producing products which are entropically more favored than reactants. And we'll say further in chapter 6, there are two parts to the thermodynamic puzzle. Change in enthalpy, which is talking about changes in bond strengths, and changes in the ability of the system to distribute its internal energy, commonly referred to as disorder or randomness, symbolized by S and called entropy. More on that in chapter 6. A reaction like this is driven by both of these changes, favorable change in enthalpy and a favorable change in entropy. But you likely also know that if you take gasoline and expose it to atmospheric oxygen, under that set of conditions, does the gasoline burst into flame? If it did, you'd be in one hell of a mess trying to put gasoline in your automobile engine. Turn on the pump and whoo! Fire! Like this stuff. Paper. Is this stuff stable in this atmosphere? Air, which is about 20% oxygen, 21%. Is it stable? Yes and no. Thermodynamically, this stuff is totally unstable. I hope that provokes the question in your mind. Well, then why is it here? Because it hasn't been supplied with the quantity of energy necessary to get this stuff to start to react with oxygen. Anybody got a Bic lighter? We flick the Bic, lit flame there, and once the combustion reaction starts, do we keep having to add flame to the system? Once you get the wood burning in the fireplace, you have to keep on throwing in lit matches? That energy barrier is called activation energy. It's province of the discipline of chemistry, general discipline of chemistry known as kinetics. And when we get more into chapter 6, I will tell you that practically speaking, there are only two ways by which reaction can be studied. Thermodynamically, kinetically. And most of what what we do in first year chemistry is to study reactions thermodynamically. Because it's a much more direct, simpler way to study reaction progress than kinetically, particularly if you're studying a very fast reaction. We've talked about, to some degree, Bronsted-Lowry acid-base reaction, which involve H+ transfer from the acid to the base. You know how long it takes, based on experimental measurement? Estimated time it takes for H+ to go from the acid to the base in a Bronsted-Lowry acid-base reaction? Nanoseconds. Telling you what, you want to measure the rate of that, you better have some pretty good measuring instruments. You know how much a nanosecond is? 1/1000th of a second. I mean, that's fast. In any case, back to this. How do we turn this skeleton into an equation? You have to inspect it. There are other ways to do it, but for now, inspection is good enough. Inspection in general means take a look at it and put on your arithmetic thinking cap. You're looking to establish material balance and charge balance. Charge balance is not a concern for this statement, is it? Because no charged particles are involved. So material balance is the only requirement which must be met to turn this skeleton into an equation, but at a glance we can see this is not an equation because of the inequality of carbon atoms, hydrogen atoms, as well as oxygen atoms, left, right. Reactant side, product side. Now then, should we, in starting to convert this into an equation, should we first speculate on a coefficient before oxygen, yes or no? No, why not? Why should we not first speculate on coefficient before oxygen?
It's in multiple products.
It's in multiple products. So how do I know what multiplier to put in front of oxygen? Because until I know how many moles of this, as well as how many moles of this, I can't decide how many moles of this will be required as a reactant. This is an arithmetic consideration, no more, no less. But when I inspect this, I see all reactant carbon atoms are part and parcel of this reactant only, and all product carbon atoms are part and parcel of this product only. That guarantees that in the equation for the reaction, the coefficient ratio of this stuff to this stuff must be what? 1 to 3. See this? 6. All right, so we'll start with that. Now, by further inspection, I see all the hydrogen as a reactant is part of this stuff. And all hydrogen as a product is part of water. That tells me the coefficient ratio of this stuff to product water must be 1 to 3. Okay? Now we're ready to speculate on the multiplier in front of oxygen. Because as things stand, I have established material balance for every other material component of this system. Well, 12 oxygens plus 3 oxygens, 15 oxygens. So my multiplier here is 15 halves. And that's what I've written down here. But, likely you've already recognized that if at all possible, we do not like fractional coefficients, even though it's a perfectly legitimate equation, there's nothing wrong with that. And when we go into chapter 6, you'll see on occasion, we have to use fractional coefficients. But more on that then, not now. For now, we'll take any equation like this, because this is now an equation, which has fractional coefficients, and multiply by the number required to convert these coefficients to strictly whole numbers. Here's the only fraction, multiply by 2, and this fraction disappears, and I get that. Enough said. Okay? Now then, see, there's another question about this system. As this reaction occurs, what happens to the number of actual particles in the system? Because I don't have any actual atoms involved in this reaction system. I have molecules of C6H6, molecules of oxygen, diatomic oxygen, molecules of CO2, and molecules of water. What happens to the number of particles in the system as the reaction proceeds? Number of particles remain the same, decrease or increase? Increase, doesn't it? Because I'm looking at, on an individual particle basis, in terms of coefficients, 17 reactant particles winding up with 18 product particles. Is this a violation of the principle of conservation of mass? Heck no! These particles have different mass. Have we not already established this statement to correspond to material balance? There's no material imbalance here. Okay. Now let's wrap up our conversation on Chapter 3 with a few more remarks on principle, system, inventory, and quantitative principle, system, inventory. Remember, a PSI, principal system inventory, is a list of the principal, the main components of the chemical system, like a solution or a reaction. Because if I'm going to understand the chemistry that occurs in any chemical system, I must know what's in the system. To try to understand a reaction without knowing what's in the system is absolutely impossible. And in many cases, I have to know the second aspect of inventory. Besides what's in the system, I have to know how much. And when we talk about how much in chemistry, the quantity to which we are invariably referring is what? A mole. That's right. That's our how much quantity in chemistry. Now then, some of these you've seen before. PSI for 1 molar HCl. All right? We'll write it over here. Remember what the PSI is for 1 molar HCl? You're in the lab, and I'll give you my marvelous Van Gogh replicate of a labeled glass with a colorless solution contained within, stoppered. Doesn't that look like a stopper? Looks pretty bad. Bearing this label, 1 capital M HCl. I tell you again that what this label means is an indication of how the solution was prepared. It means nothing more than that. It tells you that per liter volume of this solution with water being dissolved, 1 mole of HCl was dissolved as solute. That's what it tells you. That's the recipe the stock folks use, or you would use, or I would use to make that solution. Does that bottle label tell you what's in the solution? No! There's only one way you can know what's in a solution. And that's by knowing the chemistry which occurs when the solution was prepared. And if textbooks would ever learn this, they'd be a whole lot more successful in helping you folks learn stuff about chemistry. Instead, they cop out. And for this solution, they write HClA cubed. An interesting formula because it's a myth. Because in that labeled system, in that solution, you cannot detect the presence of so few as 1 molecule of HCl. They ain't there, they all reacted. So what the heck they mean with this HClAQ stuff is beyond me. They flunk! Aha! You're going to succeed. Because you've already recognized, just because we've shown you this before, that when HCl reacts with water on dissolving 1 mole of HCl per liter of per liter of solution, with water being a solvent, with products being hydronium ion and chlorine ion, respectively, the extent of that reaction is how much? 100%. And you'll study a method by which this reaction extent can be investigated. In assignment 4, 45L, and you'll be there pretty soon, the method is conductivity. Because if HCl molecules remained as such in this system, and water molecules, all the water molecules remained as such in this system, would an HCl solution be conductive? No! Because you have a system consisting mainly of molecules. They're not current carriers. And then, in chapter 4, which you've already talked about yesterday, which we'll talk about further today, you'll find out that a convenient, ready way to illustrate molar concentration is to wrap brackets around the species in question, whose concentration you wish to designate, recognizing that the brackets say moles per liter. So for this solution, I'll write this, and for the HCl solution, I'll write this. And I don't have to put an M over here. This says it. Now, if you put an M over there, it's superfluous. It's not necessary. It's not evil, but you don't need to do it, because the brackets say molar concentration. Now then, this, of course, also has a high concentration of water. More on that in a moment. Let's look at this solution. Sodium hydroxide. What do you know about chemistry of sodium hydroxide? Anybody? Is it a basic material? Why is it a basic material? Because as part of its composition it contains what? Hydroxide ion. Hydroxide ion is the strongest base which can exist in high concentration in water solution. Like hydronium ion is the strongest base which can exist in high concentration in water solution. More on that later. But do you also recognize that NaOH is the formula for an ionic compound? A salt. Salt's just a generic term for any ionic compound. And when ionic compounds are dissolved in water, at the minimum, what do they do? Dissociate. So for this solution, as for the HCl solution, the molar concentrations of the component, the principal species in the system, solute species in the system, sodium ion and hydroxide ion respectively, each 1 molar. Now, with this having been said, as a peek at chapter 5 considerations, Bronsted lowering acid base reactions which involve H plus transfer. If I mix this solution, the HCl solution, with this solution, the sodium hydroxide solution, and I tell you that this mixture results in a very large extent, practically speaking, 100% extent, Bronsted lowering acid base reaction, what do you think the reaction will involve? What will react with what? Because you see, what we got on the board, we now know what's in these solutions, right? We got our system inventory, principal system inventory. And the essence of a Bronsted lowering acid base reaction is H plus transfer. H plus transfer. Is this part of the reaction? Is this part of the reaction? Can either of these give H plus? Now this can catch H plus, minus. Anything minus can catch something plus. But I'll bet you all know that between hydroxide ion and chloride ion, hydroxide ion is by far the much stronger H plus catcher base. So what's the reaction equation? Hydronium ion, the H plus giver, with hydroxide ion, the H plus taker, and what will I make as product? Water. Done. And it all follows from this, our principal system inventory. We start by realizing what's in the system, because I can't figure out what this reaction is if I don't know what's in the system. Textbooks often represent this combination of materials as HClAQ with NaOHAQ. Flunk, flunk, flunk. That's stupid. That's wrong. But they continue to do it. And as a consequence thereof, they do not get into my classroom. Not those books with that junk in them. I don't want that stuff messing up the thought processes of you. Because you are why this class is taught. It's for you. It's It's not for UF, it's not for the state, it's not for me, it's for you. Hey, I'm telling you what, that's great. More information, quality information I can share with you, Mr. Herb, the more I will. That's what it's all about. What I can do for you. But you gotta do your part. You gotta make yourself ready to absorb this stuff by thinking about it. That's the only way. All right, on we go. One more illustration of this consideration. We're going to mix 300 milliliters, 1 molar of HCl with 500 milliliters of 0.40 molar sodium hydroxide. The question is, what is the QPSI, the quantitative principal system inventory, for this system after I have constructed it, after I mix this quantity of this solution with this quantity of this solution? We've already recognized what the reaction will be having to be. And if I study the percent completion of this reaction without stretching significant figures extensively, practically it's 100%. Now then, tell me, in 300 milliliters of 1.0 molar HCl, how many moles of hydronium ion do I have? Because this tells me, okay, if I had a liter of this solution, I'd have 1.0 moles of hydronium ion contained within, wouldn't I? I don't have a liter. I've got 300 milliliters, which is 3/10 of a liter. So I must have 3/10 of 1.0 mole of hydronium ion. All right. Well, how many moles of hydroxide ion do I have in this quantity of this solution of hydroxide ion? If I had 1 liter, I'd have 0.40 moles of hydroxide ion, wouldn't I? But I got a half a liter. So how many moles of hydroxide ion do I have? Now you can work this all out with dimensional analysis. And indeed you should, if you need to do so to follow the arithmetic. But we just did it in quick fashion in order to realize that when I make this mixture, I have an abundance of this stuff, don't I? So in running this reaction, practically speaking, which reactant gets killed entirely? Is it this one or this one? Which one is it? Hydroxide ion. So what we've also just talked about is an illustration of what's called limiting reagent or limiting reactant, more chapter 4 stuff. So after I run this, I will make, or on running this I will make, because of its 100% efficiency, how much water? How much water will I make? I'm listening. Because what I'm really doing is putting together 0.20 moles of this with 0.20 moles of this to make how much water? Now I do this stuff on purpose because I know that when it comes to thinking arithmetic in your noggin, you likely need practice. If in high school you did arithmetic with calculators, did you? If you did it wrong. Our language is two-part. I've told you this before. Numbers and letters. Alphanumeric. insist on doing arithmetic calculator, you will not learn the numeric part. And that's a serious detriment in science class, because you need to be able to think in numbers.
What would the final answer for that problem be?
We're not there yet.
Oh, we're not there yet.
No? Okay. So I'm going to pester you regularly to think in numbers. With the best calculator you got, that's this. Not that thing you put buttons on. All right? So tell me, after the reaction runs, what is our QPSI? Will we have some of this left? How much? Will we have some of this left, practically? None. How much of this will we have? Well, by golly, that's a tough question, really. Because we have 800 milliliters total solution volume. And in this solution, we just made 0.40 moles additional water. How does this 0.40 moles of additional water compare to the amount of water I had in the system originally on making this mix? I got 800 milliliter system volume, with the main system component being that. Question. Let's go back to the lab. I'll draw another flask. 1 liter. H2OL. What's the quantitative principal system inventory? We know the principal system inventory without quantifying it is water. Okay, so far? How much water? How much? What I'm really asking you is, tell me the concentration of water in pure water. And if I have a liter of water at this concentration, in 1 liter, how many moles of water do I have? You think it's a lot of water? You know that the molar mass of water is 18.0 grams to 3 sig feet. Did you recognize from our swimming pool problem that practically speaking the density of water liquid is what? 1 what? I mean, if I ask you how tall you are and you say 14, well, you haven't told me anything. You leave off the units, forget it. I don't care what else you say. No good. Means nothing. That's why I tell you in doing dimensional analysis problems, all calculations in science class have to be done that way. You better first pay attention to the units. Because anything else is meaningless. So let's think about it. 1 mole of water has a mass of 18.0 grams. And the density of water, practically speaking, this. But I'm not dealing with a milliliter quantity, am I? I'm dealing with a liter quantity. How many milliliters in a liter? Okay. Now, please examine the units. Is it moles per liter? How about that? And if I divide 1,000 by 18.0, the 2 sig figs, I'll get 55. That's how many moles of water in a liter of water. So in this 800 milliliters, which is practically speaking water, if I multiply 55 by 0.8, I have a pretty good approximation of moles of water in this system, don't I? Now, we want to be really careful about this. We won't now, but in the future, when we want to be really careful about this, we're going to have to figure out what the volume of this system is occupied by the presence of sodium ions and chloride ions. Because we didn't write that down here yet in our inventory, did we? For this system. Because we got 0.30 moles of chloride ion. They're in there, they didn't do anything. And we have also 0.20 moles of sodium ion. Is this charge imbalance? Hey, don't forget this 0.10 moles of hydronium ion that's still in there. We've got total 0.30 moles of plus and 0.20 moles of minus. And if I evaporate this solution to dryness, what will I obtain? If I evaporate this solution to dryness, what will I obtain? Oh, let's put it this way. If I evaporate the solution to dryness, what solid will I obtain? Sodium chloride, how much? How much sodium chloride will I get from this system if I evaporate everything from the system except the resulting solid product? 0.20 moles of sodium chloride. What will happen to this other 0.10 moles of chloride ion? It'll be driven to recombine with hydronium ion to make HCl vapor, which will go away because I've boiled it off. More on that kind of stuff later. On to chapter 4. Now then. We got a good start with chapter 4 yesterday. Where you are introduced, first of all, to our chemist's main unit for counting, the mole. So just for fun regarding mole, take a look at page 4.3 at the bottom, question 4.3. Atoms, ions, molecules. And in addition to the mole, you learn this number, didn't you? What's the name of this number? Avogadro's number. When Avogadro reasoned that for moles of molecules, it didn't make any difference what the molecule was. CO2 molecules, water molecules, who cares? He had this number. It took 80 years after he made this recognition for the scientific community to accept his recognition. 80 years. Now I'm going to write particles per mole. Fun question. Is this a big number? Yes. It has been calculated that if I had a limited fleet of flying boxcars, you know what flying boxcars are? These planes that can carry a whole lot of cargo. Okay. An unlimited fleet of flying boxcars, all filled up with baseballs. You all familiar with baseballs? And we imagine the surface of the earth, the entire surface of the earth, to be of uniform altitude. No valleys, no mountains. Okay? It's one uniform surface, all sea level. The flying boxcars have a job to continue to fly around the earth, depositing that many baseballs in uniform layer on Earth's surface. Do you think that would cover the surface of the earth entirely? Not only will it cover the surface of the earth entirely, and you can do the arithmetic to prove this, it would give you a layer of baseball 60 feet deep. That's a lot of baseball. Take a whole lot of time for some character in Major League Baseball to fall off that many. All right? A mole of helium. What do you know about helium? Is it a molecular stuff? It's atomic stuff, isn't it? So in a mole of helium, how many helium atoms do you have? How many particles do you have? That many. All right? How about a mole of elemental nitrogen? How many particles do you have in a mole of elemental nitrogen? How many particles do you have? In a mole of elemental nitrogen, a mole, how many particles do you have? Individual particles. We've got that many. Because these N atoms are stuck together in each other, right? With a strong N-N triple bond. The particles are nitrogen molecules. Now, if I had a sack of nitrogen molecules, one mole, and I shook it so strongly that all the nitrogen bonds broke, then I'd have twice that many particles. Nitrogen atoms. But not until I break the bonds. All right? Now then, how about magnesium bromide? How many moles of particles in a mole of magnesium bromide? Moles of particles. Now we're asking you if you recognize that magnesium bromide is an ionic compound. And remember that ionic compounds are composed of what sort of fundamental particles? Ions. So in one mole of magnesium bromide, what's the formula for magnesium bromide? Huh? What is it? How many moles of particles in this mole? How many? How many moles of particles in the mole of this stuff? 3! 1 mole of these ions and 2 moles of those ions. Okay? 4.4 grams of carbon dioxide we'll do next time.